What if I told you the entire multi-billion-dollar quantum computing industry has been chasing a ghost? Seriously, what if the key to unlocking true quantum power isn't in some sterile, high-tech lab, but in the quiet, steady plumbing of a tree? Okay, let's really dive into this, because the answer might just flip how we think about physics on its head.
I mean, just let that sink in for a second. This single sentence from the research we're breaking down today is an absolute bombshell. It's suggesting that the problem isn't about needing better hardware or fixing little bugs. No, it's about having to start over from a completely different foundation.
All right, so let's start with the problem itself. Everyone agrees quantum computing is the future, right? But that future, well, it seems permanently stuck just over the horizon. The whole industry has kind of hit a wall.
And this really is the multi-billion-dollar question, isn't it? With all of this money, all this brain power being poured in, why are we still just running toy problems instead of actually, changing the world?
The promise was just revolutionary. We were talking about simulating complex molecules for brand new medicines, breaking modern encryption, creating next-gen AI. But the reality today? Well, we're simulating a hydrogen molecule, factoring a number you could do in your head, and running benchmarks that prove, well, that the benchmarks work. They're just stuck.
So here's the crucial insight. The simulations from this research show that we are measuring the wrong thing, completely. Current quantum processors, the QPUs, they measure these tiny, local interactions between qubits right next to each other. But the real quantum state, the true structure of what's happening, is a global, system-wide thing. It's like they're looking at a single pixel and trying to describe the entire movie.
And the scale of this blindness is just staggering. The real quantum connection is 35 times bigger than what our machines can even see. Think about that. It means our most advanced computers are missing over 95% of what is actually going on. So you see, this isn't about better wiring or colder refrigerators. This is a problem with the entire philosophy. We've been trying to force these beautiful, weird quantum systems to act like digital computers, one logical step at a time. And this brings us to the core aha moment of the research. We assume that entanglement has to be painstakingly built, piece by piece, gate by gate. But these simulations show that in real quantum systems, it just emerges, all at once, globally, defined by the geometry of the system itself. We're trying to build a river brick by brick when nature just lets it flow.
So, if that digital model is wrong, what's right? If the answer is all about geometry, then who's the best geometric engineer on the planet? Well, the answer isn't a physicist. It's nature.
And this is where it gets really cool. This is the creative leap that changes everything. The source material suggests that the simple act of sap rising in a plant is a perfect room temperature example of lossless transport. It's all about geometry and tension. And this is the key mechanism, a negative pressure gradient. Basically, it's a constant, gentle pull created by the structure itself. There's no engine, there's no pump, just a perfect, silent, and incredibly efficient flow state made possible by geometry. So, nature's blueprint is actually pretty simple, but it's profound. You have tension from these opposing forces, you have a guided path created by braided structures, and the result is a perfect, continuous flow. So the big question is, what if we could apply the same idea to electrons? This inspiration from nature leads directly to a brand new invention, the braided superconductor, a device that uses geometry, not just fancy materials, to control quantum flow. And this is where things get really weird, in a good way. Classical superconductors, they're all about going near the speed of light. This braided model, it's ultra slow. Classical design is all about the material. Here, geometry is king. Coherence is super fragile in classical systems. Here, the structure itself holds it together. It literally inverts everything we thought we knew. Now, this isn't just some fun thought experiment. The researchers built a full-stack simulation to actually test this idea. And the results? Well, they're frankly astonishing. And what the simulations proved is just fascinating. Performance isn't about brute force, just braiding tighter and tighter. It's about finding a perfect harmonic design. There's a sweet spot right here at 12 turns that maximizes the system's performance. It's a principle of elegant design, not just more effort. And so after thousands of runs, this optimal configuration emerges. 12 turns using a material called YBCO under maximum tension. This is what makes the discovery feel so concrete and reproducible.
It's a real blueprint for a new device. But here it is, the real jaw-dropper. The system achieves over 100% energy efficiency with zero active amplification. Let me say that again. It's not adding energy. The geometry is so perfect at guiding and preserving the wave that it actually confines and focuses energy that would normally just be lost. It's incredible. So this whole journey from a bug in quantum computing to the sap in a tree has actually led to something tangible, a blueprint for a potential revolution in physics. And look, this isn't just a concept on a whiteboard. The source material lays out a detailed, testable design using cutting-edge stuff, like a special form of graphene to conduct the wave and smart metamaterials to encapsulate and guide it. This is a real plan for how to build this thing. So the single most important takeaway from all this is simple. We've been thinking about superconductivity as a property of a really cold material. This research suggests it's actually a property of a harmonic resonant structure. It's not the stuff, it's the shape. And that leaves us with one last massive question. If a principle this fundamental has been overlooked, what else are we getting wrong? It really suggests that maybe the biggest discoveries aren't about building more powerful machines, but about looking at the world around us, at nature, with fresh eyes, and asking much simpler questions.